Okay, there we go. Okay, so we're going to be going over the example that I introduced back on, I guess it was last Thursday, which was our problem 2. So I guess first I'll just remind you what the nature of the problem was, just briefly, and then go into the approach for implementing it. So just remind you here. So we're talking about Actually, let's go down to the study design here. We're dealing with some results from a phase 2 dose finding trial in cystic fibrosis patients. It was parallel design with 100 patients per dose arm, and there's different doses then of ME2, so corresponding to our different treatment arms. So we've got a placebo group, one at 20 milligrams per day, another at 40, and another at 60 milligrams per day. And that's administered by inhalation over 24 weeks. And what we're going to be looking at is the occurrence of moderate to severe coughing spells. And in this case, we're going to look at it on a longitudinal basis. So we're going to take reports of these coughing spells for each one of the 4-week intervals between visits. So the design called for visits every 4 weeks over that 24-week period. So we've got, what is that, 6 visits, at which we have reports of whether or not they experienced a coughing episode during that time. So as a result, we're going to have then some longitudinal binary data that we're going to be analyzing. And because it is longitudinal and we have multiple observations for each individual, we'd like to account for any variability across the individuals, or equivalently, we want to account for sort of correlation within individuals. So we're going to be treating this as a mixed effects model then, where we account for that variability amongst individuals in some manner. Okay, so we're going to construct that model. The data set we're working with, let me open that up. You can see the file name there. Where'd it go? Here it is. Open that guy up. Okay, let me make it big enough to see. I can't even see that. Okay, so we've got a fairly simple set of data. I didn't incorporate any additional covariates in here, but you could imagine, different possibilities. But for now, we'll just keep it fairly simple. So we've just got a patient identifier, the dose that was assigned. We've got the time. In this case, it's the endpoint time. Well, it's actually the visit time. And then we have a report of whether or not coughing occurred during the 4-week period prior to that visit. So, for example, here, the first 0 you see here, which occurs at time 4, actually means that's indicating that no coughing episodes were reported during that 0 to 4 week period. Similarly, this one here says that that patient did have at least one coughing episode during the period between 4 and 8 weeks. So again, these are reports over intervals. And you can see right here, for example, I've highlighted the data then for a single patient. And all of these patients then have, in this case, I made it a fairly trivial simulation where we don't have any dropouts. So we've got 6 observations then for each individual, and you can see a mix of behaviors here. Like this is a placebo patient. You can see they had one coughing episode during the second interval. Here we've got a patient on 60 milligrams per day, and they had a couple episodes here sort of in the middle. Then you have another patient here who can't seem to stop coughing. Here they've got coughing episodes during each one of the intervals. So you can go through and see a variety of patterns then of whether or not coughing has occurred during these various intervals. The net result we can see from some exploratory analysis of this, where instead of trying to make sense out of the binary things alone, we can count up the number or fraction of patients that experience coughing episodes during each one of these intervals and at each dose group. So we can see things like, here, let me open these up. Okay, make it big enough to see. So for example, here we're looking at fraction of patients with a cough versus dose. And for each time period here, for each visit, we've got a point here for the fraction of patients that are reporting cough. And you can see in general this is going up with dose, though there seems to be some sort of pattern. You can see where on the 4-week episode, that's the top curve here, there's more frequent coughing than there is for the remaining time points in here. And if you just turn the data around and instead plot it as that same fraction versus time with separate curves for each dose group, again you can see the pattern here over time, maybe a little better. And you can see, for example, for the 60 milligram dose, the green one here, it starts up high and falls off and levels off here after around the 12-week, beginning at about the 12-week visit here. It actually looks like it might even level off a bit sooner when we look at a couple of the lower dose groups. And not surprisingly, the placebo group is roughly level in here. Though, as you can see, when we're working with binary data, that even though we've got 100 patients contributing to this, the fractions here have, those statistics have a fairly high degree of uncertainty about them. Okay, so let's move on to how we might model it. And here, let me bring up the model I had proposed. Let's go ahead and bring this full screen. Okay, so this is the one I had proposed to you. Again, it's going to be a binary model, but it's going to be a mixed effects binary model where we're going to incorporate a random effect on at least one of the parameters here. And in particular, well, let me actually start at the top here. So the basic model here, it's binary, so the basic model here is, or the basic likelihood is going to be Bernoulli, where there's some probability. Here I'm using I to represent study period and J to represent patient. And so we've got a probability of cough, which can vary both by study period and by patient. And then the proposed model here for that probability here is the logit of that probability is this thing over here. And recall, we're trying to incorporate that time dependence, that apparent tolerance to this coughing effect here, using a model here that was based on some old work here by Porcher. So we've got a baseline term in here. Actually, I probably shouldn't call it base. Well, it is baseline essentially in this instance. So that's you can also think of it as placebo effect, I suppose. But in this case, we're assuming. In this case, I haven't incorporated any systematic placebo effect. I'm assuming baseline and placebo are essentially synonymous. We could get a bit more sophisticated, I suppose. And then what we've got is a model that's linear for logit of that probability is linear with respect to the dose, except that it's further adjusted by a term down here to account for the tolerance. And we've got a couple terms here. The thing in the denominator here called x50 is a is related to the tolerance. It's just a fixed parameter there. And then we have on top here, this x tall ij is actually a function, and in this case a function of both dose and time, and that's described right here. And you can see it's just set up in such a way that it actually starts out at 0 at time 0, because this term on the right would just vanish when Tij is equal to 0. And so in the case, so at baseline, essentially it's saying the dose response, or at time 0, it's saying the dose response would be a simple linear one. But as time goes on, we introduce some nonlinearity, and the degree of tolerance is well, the degree of tolerance is going up. In other words, the magnitude of the effect will be going down. So this x-tol term is getting larger with time, so the overall value of that term then is getting smaller. So we would expect to see a decrease in cough if that's the case. And here I've incorporated a random effect in only one parameter, the baseline value here. And just kept it simple here. Just made it normal with some mean value and some variance here that I called sigma squared for that baseline. Maybe one comment I don't think I made the last time is you'll probably find that when you're working with binary data, you'll find it's pretty hard to support much more than one random effect in most cases unless you have a particularly rich collection of binary data within each individual. In this case, where we've got, I guess it's 6 observations per individual, it's unlikely we would be able to reliably estimate more than one random effect in there. And that's because binary data, in a sense, is kind of information poor. And so unless you get a whole lot of it within each individual, it's really hard to estimate multiple individual specific effects in here. Okay, but we're going to incorporate that one random effect on our baseline. I suggested some weakly informative priors here. So we've got mostly some fairly flat priors on things. We got our E0 is just going to be a fairly flat normal here. Same thing for alpha. Actually, in hindsight, I'm not sure that was the brightest choice in the world. I think it would be pretty reasonable to have assumed that alpha would be non-negative for this particular case, but actually we find that it probably didn't make too much difference putting this as the prior. Then I did assume that x50 and the k-tol were non-zero. So here I've put these fairly flat priors on the logs of those parameters, and then finally for sigma I used a uniform that starts at 0 and goes up to a relatively large number. Alternatively, I could have picked something like a gamma or maybe a fairly flat log normal for that, much like I did some of the others, and those would have also been plausible priors for the sigma. Okay, let's see, and then let's actually go ahead and implement this thing. Let me sort of put that off to the side here. We can probably close this guy too. Now, yeah, the versions of the model that you have are named hands-on2.txt for the WinBUGS model and hands-on2.r for the for the R script. I've renamed them here because after running this I decided it needed some tweaking, but the versions you have are the ones that I've called hands-on2 ORIG for original for these two cases. So let's start with those because it's probably a nice learning exercise to see why I decided it did need some tweaking. Okay, so let's start with, let's go ahead and open this up, the model first. Okay. Let me make that a little easier to see here. A couple things here. Oops, must have picked the wrong thing. Okay, make it bigger. Okay, that should be a little easier to see there. Okay, so this is a rendition of the model that we just saw right here. So let me see if I can relate the pieces to each other here. So the first component here is just our likelihood. So where I over here called it I cough is being Bernoulli with some probability. Well, that's this line right here where The way I've set it up is the data is just called cough, and again that's just going to be 0 or 1. And then that's distributed Bernoulli, again dburn in Bugsies, with some probability. I called pcough, and then I, and this is all embedded inside of a loop that goes from 1 to however many total observations we have in here. So that's our basic likelihood. As I'm saying this, it might be worth me actually going back and showing you the data structure here, so that you kind of know what's data and what isn't in here. Let me actually open up the R script too. Let's see. Okay, so you'll find the R script again is going to be structured very much like the last couple examples I've done. In particular, it should be fairly similar to that mixed effects example I showed you before. So we've got our name in it. Actually, when I ran this originally, it was hands-on 2. I haven't reset it up to say hands-on or ridge. I probably should. And then we have a bunch of junk here that's just more bookkeeping. We won't worry about that. The part I wanted to get to was the data set. So the first thing is I've got to read it in. So I'm just using the read.csv function here to read in the data. And this is where those exploratory plots were done. We can skip over that. And a couple of things here. One that I'll point out is that in some cases you may have whatever your individual is, whether it be an individual patient, an individual study, or what have you. We need to have an indicator variable, an identifier for that individual. In this case, it's our various patients. So we've got, 400 patients, or is it 400? Yeah, I think it's 400 patients total in this study. So we have to have a unique identifier for everyone. And the way we're going to use that identifier in the BUGS model is they have to be in an integer sequence beginning at 1. So it has to be 1, 2, 3, 4, and so on up to 400 in this instance. Now, in many cases, you may get a data set where that's not the way it is, where even if patients were originally assigned that kind of an identifier at the beginning of the trial, not all patients completed the trial, or things like that, so you'll have gaps in it, or they may give names that are completely different from a simple integer. So we need to convert them to 1. Now in my case, the data set they actually were, so you wouldn't have to worry about it, but in general you might have that. What I've shown you here is one particular trick for using R to convert whatever that identifier is to an integer sequence. So I've taken the patient column that was in our original data set, and the trick here is you use as factor to convert it to what R calls a factor, which under the hood, a factor is a combination of two things. It's got a label, which is equal to whatever that original value is, but then under the hood it also has an identifier, which is a sequence of integers. But whenever you look at it in R, you just see the label. But if I then, in addition, then say as numeric after that, it will convert it back to an integer, and now I will have a nice integer sequence that starts at 1 and goes up to however many patients I have, which is exactly what I want. So that's one little trick for doing that. The other thing is in looking at this model, I realized that, okay, I really don't have measurements taken at a particular time. What I actually have is the report of whether or not an event had occurred over an interval of time. The approach I chose to use to keep this simple is instead of using the time that's in our data set, which is the visit time, which is really at the end of the interval where the observation is relevant, I instead used a midpoint time. So that's kind of a quick and dirty way of using the approach I've got here. Now alternatively, something we'll be talking about more when we move on to the time to event modeling, I could have chosen to model the hazard of having a coughing event, which is a continuous function over time, and then to construct the probability of having an event occur over a particular interval involves taking the integral of that hazard function. Again, that would be an advanced topic at this point, and something we'll leave until we get to the time to event modeling exercises. So for now, I'll get a little more quick and dirty. So I'll substitute the midpoint time for the Tij here, and all this is doing right here is just going through and stepping through all of the patients and calculating the midpoint times for each one of those observations. So now the 0 to 4 interval will be represented by a 2, the 4 to 8 by a 6, and so on. And that's the value that I'm going to use down here inside our actual data component here for our time. So it gets named time again here, but it's now going to be a midpoint time. So the data I'm going to finally pass to BUGS is going to be the number of observations, the number of patients. I'll have my patient identifier, the time. Again, this will be a midpoint time, the daily dose, and the 0 or 1 indicating whether or not they experienced a cough. So that's what's getting passed to BUGS. Whoops, I just flew by something I wanted to look at. Okay. Then we've got to provide. Let's see. Let me go back to the model now, because mainly I wanted you to see the data at this point. Okay, so I mentioned we've got our Bernoulli statement, our likelihood in terms of the Bernoulli distribution. Then I've got to describe this function here. So our logit for our P cough here, our probability of a cough. So I've got my baseline value, and more on this, what's going on here in a second, plus our alpha times dose over our 1 plus xtol over xtol 50. So that's just a statement in BUGS terms of this component in our model. And then I have to specify my xtol component here, and that's going on right here. Again, that's in terms of our midpoint time. And that's really the core then of our likelihood, except for one more piece, and that's dealing with our interpatient variability in this in our baseline value, and that's going on in this other loop on top, which is looping over all of our patients to generate a random effect for each one of those patients. So that's where you see again our E0. It's going to be normal with some mean, and again with BUGS, it's going to be in terms of precision in here, which is again 1 over the variance. So that will take care of that. But then in order to reference the appropriate patient in here, I have to include that patient identifier in the data set, and recall we did include such an identifier, and use that, as you can see right here, to index the E0 inside this loop that goes over observations. So that's how we incorporate our subject-specific random effect in here. Okay, so that's really the core of our likelihood, and then we've got to specify all of our prior distributions down here. And here you can compare to what we've got on the right-hand side. So we've got our, what I called E0 hat is the same thing that's called E0 mean over here in BUGS. So, and that's normal, 0, 10 to the minus 6. And again, because it's using 1 over the variance, so it's equivalent to normal 0, 10 to the 6th, where 10 to the 6th is a variance. Same thing for alpha. And then you can see we've got things like the log of our, what I called xtol 50 here, called x50 on the right-hand side. Again, that's our normal 0, 10 to the minus 6th. Same idea for the k-tol, our rate constant in there. And then the other statements here you can see are just things to convert it back to the anti-log here, in this case for both xtol 50 and ktol. And then finally we've got over here, you can recall I was doing a sigma being uniform 0 to 10 to the fourth, and same deal right here. And this statement is just converting that to a precision. Okay, that's actually now enough that if we ran that model with appropriate initial estimates, we'd have enough to get MCMC samples for all of the model parameters. But as usual, we're also going to want to get some predictions that we can use for doing some posterior predictive checking, and that's what's going on with the remaining statements in here. So we can see we've got right here is what we could call our individual predictions. In other words, posterior predictions for new observations in the same patient. So in that case, it's just a repeat of the original likelihood statement up here, but I just give it a new name so that the thing on the left-hand side is no longer a data item. It now becomes a predicted value. And then for our population prediction, or again, this is a posterior prediction for a new observation in a new patient who's getting, in this case, the same dose and being observed at the same time as the original patients, I have to, in addition to having essentially the same likelihood function, the right-hand side changes because I've now got what I've called peak-off pred, which is now a simulated value for an individual specific random effect in here, and so I have to calculate that using a simulated value for the baseline value, our E0 pred, which I have to in turn generate up here within the loop that's looping over patients. So that'll give us both our individual and population predictions in this instance. So that's our WinBUGS model. So I guess the next thing is we have to provide some initial estimates and then run it. Let's take a look at that. So let's take a look at bugs in it right here. So it's starting right here. So what I've done in here is use some summary statistics to try and get at some of the values here. So for example, for E0 mean, I went ahead and I'm going to randomly generate values here so that I have different starting points for each one of my chains. But I went ahead and for my mean, in this case, I used the observed fraction of patients that have a cough in the dose equals 0 group to come up with that. And I also did where am I going here? I got to remember what the heck I'm doing here. Oh, okay, that's right. I'm trying to remember some of the specifics here. Here I'm also taking a standard deviation of that statistic in here to try and get at some of it, and using that, so that gives me my initial estimate on E0 mean. For the other cases, I guess also made some attempt at it by using some information at the earlier doses to get some, or earlier times to get some idea on what alpha might be. So these are very crude, but they at least get us into the broad ballpark. Then for xtol, there it was a real seat of the pants guess. I'm looking, it looked like the X50 might be somewhere in the neighborhood of the doses that we're using, so I just put in a value of 20, which is the lowest dose we've got in here. So that was a very crude guess there. Ktol, it was a similarly crude guess looking at the time that we have in here, but I picked a value that was at least in the neighborhood of the time values we're looking at. By the way, here I've got 0.4s. Since these are log transform, these are approximate CVs, so we're talking about pretty much roughly 40% CVs for those two quantities. And then finally, sigma, again, was a very crude number that I put in there. And then ran them, basically using those, so you can see deciding what, whoops, did it again. Deciding what values do we want to save. Well, I certainly want to save the core parameters, which will be the mean baseline, my alpha, xtol 50, ktol, and sigma. I also wanted to capture the individual specific baselines as well as the posterior predictions. I could see possibly also being interested in calculating the predicted probabilities, which I didn't do here, but that would have been a reasonable thing to consider capturing too. And then we pull it together, we run it. Just started out with the usual 3 chains, 10,000 per chain, burn in for 4,000 as a starting point to see how things were doing. Got our usual sort of standard stuff for getting some of our summary plots. And then down here, oops, stop there. Here we go. And then down here, getting some posterior predictions and comparing those to observed data. In this case, again, trying to look at posterior predictions of binary data all by itself is very difficult to interpret. But in this case, we can break up all the observations by dose and time and look at the fractions of patients experiencing a coughing episode for each one of those. So we've got a nice summary statistic to work with, and we can look at the predicted values for that same fraction. Let's see, I got a question here. Let's see. Can you explain X50 and how to give the initial estimate again? Okay, I've got to actually think about this. It's been a while since I thought about exactly what it would be. It would be, let's see. I guess that would be the dose at which tolerance, let's see, let me think before I speak here. Okay, let's see if we got dose go to infinity. I want to say that it's the dose at which the tolerance would be half maximal. Let's see if that's actually true. Okay, if I put x50 on top, multiply it here, I end up with x50 plus xtol. Yeah, I believe that's true. Trying to think that through with an audience is always a little bit tougher, but I believe that is true. But it relates to what it in effect relates to what sort of the maximum potential magnitude of the tolerance would be in this case too. Is that true? Let's see. I think I need to think that through a little bit better here. I don't remember the exact value, and as a result, I would need to think that through properly before actually giving you a firm answer on coming up with the mechanism for initial estimate. So rather than try to think out loud in front of everybody, let me do that after the fact and maybe give you a reply later, rather than getting stuck on that for the moment. Because there is a way to think it through, and I'm just not doing so in real time very well. If somebody comes up with a bright idea they want to share, go ahead. But I just don't want to get stuck on that. Okay, let's go ahead and move on for the time being, and I'll revisit that. Okay, so what I'm going to do here is take then our posterior predictions. First, I'm going to take the individual predictions, and the next step here is to take the is to calculate the fraction of patients that experience cough, both for the observed data, and then in this statement down here for the for our model predictions. Now, of course, the model predictions, I'm doing that for every one of the MCMC samples, and then calculating the 5th, 50th, and 95th quantiles or percentiles for those predictions on each one of those, because we're going to plot those, and pulling that all together, and then plotting that in a couple of ways down here. And so we'll do that. And then the next step in here is to just do the same thing for the population predictions. So this is actually identical, except that it's population predictions. And then finally at the bottom, I just did a sort of a real quick and dirty look at the distribution of the E0 values, doing, which ones did I do here? I did oh, actually, that's right. You don't see it. The QQ-hist function generates what's called a QQ plot as well as a histogram of those quantities here, so you can get some idea what the apparent distribution is and whether or not it's consistent with the assumption we made that it was normally distributed across individuals here. So that's our basic function there. So I'm not going to run that this in real time. I didn't time it exactly, but it does take, I don't know, I think it takes somewhere on the order of 10-15 minutes for this thing to run, so we don't want to sit here and watch it, so we'll use the Julia Child approach here. I'll take the one out of the oven I did before. And that is right here in what I call the hands-on to orage here. Let's take a look at the plots here. Okay, here's the history plots for our key parameters in here. And yeah, and there's a couple of the parameters that are okay. Sigma is fairly good. E0 mean is reasonably good. I might want a few more samples, maybe increase the number of iterations to clean it up a little bit. But alpha here, K-tau and X-tau 50, particularly alpha and X-tau 50, are not looking so good. You've got extreme extreme autocorrelation present. They definitely don't look like fuzzy caterpillars using this number of samples. And you can see some extreme things happen. Notice this green on X-tau 50. If you look at the green chain here, notice that at some point it basically just drops to 0 and pretty much stays there. You see a similar pattern with the K-tau with that same chain. So we've got, and alpha does some ugly, alpha does pretty much the same thing. So we've got some fairly ugly behaviors where we really don't have convergence amongst the chains, and within the chains the autocorrelation is extremely severe. So there's a few issues that could bring about something like that. One possibility here is just that we have a significant identifiability problem. That's the same sort of thing that'll lead to if you're used to using NONMEM, often that kind of identifiability problem will show up in symptoms like stopping because the number of significant figures is falls below a certain level, or also if you're often the covariance step will fail because of identifiability problems like that. So that's one possibility. Another possibility that I suppose could also be sort of labeled as an identifiability problem is what we see as a result of this extreme behavior where some of these chains are essentially being driven to zero, so we end up with a sort of degenerate form of the model. And once it gets there, it seems to kind of get stuck there. And if you look at the deviance, which is kind of a measure of model fit in here, again, that's minus 2 times the log of the likelihood, it's not that different for the different models. There's maybe a hint that maybe the green one is a little higher on average than the others, but it's there. Again, lost there. There we go. Again, that might hint at something like an identifiability problem. But basically, it's saying that this degenerate model seems to fit the data. Not great, but maybe not so bad. So again, that's an identifiability problem of sorts. Now, so part of the question that might be is, okay, do we have reason to reject that degenerate form of the model? If we do, we could restrict our priors. We could set up our priors in such a way to make that degenerate model impossible, and see how that does. But that is a form of incorporating an informative prior, and we'd have to decide whether we find that accessible. But anyway, at this point, we have something which is not acceptable for any probabilistic inferences at this point. So my tendency here would be to say I need to do something about this. Also another thing that can happen that can induce things like this is sometimes if you have fairly extreme correlation amongst some of the parameters, which in itself is a sort of identifiability problem, sometimes you can reparameterize the model and it will do better at that point. I'm not sure that's going to do it in this case. There is some correlation amongst some of the parameters, but it's not as gross as I've seen in some other instances. So I'm not sure that would resolve the problem. So anyway, but given it the way it is right now, it's probably not something I would want to make inferences based on. On the other hand, it does a reasonable job of fitting the data. By the way, I'm going to show you some of the other plots here. This is what the marginal distributions look like for the MCMC samples were generated. Again, since they clearly haven't converged, they're not to be taken too seriously, except maybe as a diagnostic that some funny things are going on. Here, for example, in the K-tall, that sort of bimodal thing where we basically got one of the chains is essentially driving K-tall to zero. That shows up right here as that degenerate case, but then you have a fairly smooth distribution for the remainder of it that looks maybe a bit more plausible. So that's kind of comes out of there. If we look at the Gelman-Rubin-Brooks plots here, we start seeing those, we can see the convergence problems there, though I'm not sure this tells me a whole lot more than the history plots already did. But you can see some of these numbers are substantially bigger than 1. Deviance is no problem. That's still fairly well below 1. But when you look at, again, alpha, X-tall 50, and K-tall, you've got numbers that are well above 1 and indicating some convergence problems. Again, as I was saying, now it fits the data reasonably well, but the inferences about any of the parameters would not be very credible in this case. So I did take one strategy on this to to try and modify that. And that strategy was mainly to take a couple of the parameters that were being most problematic in terms of in terms of that sort of degeneracy and restricting them. In particular, I put a lower bound on both the KTOL and the X50 parameters to keep them from being sort of driven to zero and collapsing the model as a result of that. By the way, one of the reasons I suspect we're having trouble with those is if you look at the time plots on here, notice that things pretty much reach a sort of an equilibrium here, a steady state. It looks like most of them pretty well get there by around that 8-week point. So you can see, in fact, you can see by, for the 40 and 20 milligram dose groups, it looks like you're high at the first one, and then after that it's fairly level. There's maybe 60, maybe a little higher, but the point is there's limited information about how quickly this thing is actually falling off in here, and I think what we were looking at is a reflection of that, what's actually a pretty high degree of uncertainty on how quickly this falls off, and that KTOL is not all that well determined by the data. Okay, so I'll show you the strategy I use. Let's go ahead and close that. Let me open up a revised version of this. Again, we'll open up both the model and the R script. Okay, so in the model, the top part of the model is unchanged. So the basic description of the model is unchanged. It's the prior distributions that have been altered. And in particular, what I've done, as you can see, I've actually left the original priors in there and just commented them out. But now I've replaced that fairly flat prior on the log of XTOL50 with a uniform for XTOL50 that goes from 5 to 20. So I'm staying, basically I've gone, I've pulled it up from 0, but it's, in this case, it's a fourth of the lowest non-zero dose we have, and then I stuck an upper bound on it. Both are somewhat arbitrary, but basically I wanted to start above 0, but somewhere below our dose range studied, and somewhat above in here. It's what's optimal I don't know, and if we were going to use this for formal inference, I'd like to do a sensitivity analysis on some of these choices. And then for KTOL, a similar strategy here. I put a lower bound on this and an upper bound, and the main thing is I wanted to restrict, more than anything else, I wanted to restrict that lower bound so it's not being pushed down to 0. So that's the basic change to assess how that performs. And what we see when we do that, I guess the other comment here on that, the only change of relevance here really is what I did with the initial estimates. Let me go back up to those. Okay, again, I left the original code in there, and now I've just changed it, and I've actually used pretty much the same initial estimates, except I used a truncated normal distribution and truncated the distribution at the same limits as the limits I put on the priors, and that's just to avoid what had happened is if you gave WinBUGS an initial estimate that was outside the bounds of your prior, it would throw an error and would quit running. So this just prevents that from happening. So I do that for both the XTOL50 and for KTOL in this case. and ran that. That's the only difference in this case. And when we run that, it's in this one now, hands-on 2. Okay, come on, there we go. Okay, and at a pretty quick glance, you can see things are looking quite a bit better from the standpoint of convergence and mixing of the chains here. Again, I still use, this was still the 10,000 iterations with 4,000 burn-in for each one of the 3 chains. And as I look at this, I see it's looking reasonably good. Optimally, if I'm going to make any inferences about particularly alpha and xtol 50, there's still a fair amount of autocorrelation present. In here, so we're not quite a nice fuzzy caterpillar there. In this case, rather than modify the model further, I'd probably just run more MCMC samples to offset that autocorrelation. Doesn't eliminate it, it just means that you'll end up with enough samples with to make more precise inferences about those particular parameters. So this one is now looking fairly reasonable, certainly much improved. The only thing one has to ask oneself when we go through that is whether or not the assumptions we made to get there, mainly eliminating that sort of degenerate model case, was really appropriate, or whether we should actually be entertaining something like a mixture model that actually explicitly admits that degenerate case as a possibility. But at least for this example, I just went ahead and sort of eliminated that degenerate case by putting some lower bounds on these, and I suspect it was the lower bound on k-tol that made the primary difference. Now we can look at our marginal our marginal posteriors here, all looking quite plausible. We've eliminated the degenerate case in k-tol in this case, of course. And actually, because this is a smoothing sort of thing, when it creates this density, there's actually a truncation in effect that occurs at 0.05 roughly. Where is that? I guess roughly about where I've got the cursor in here. So again, all the rest of them are looking fairly plausible. If we look at our Gelman-Rubin-Brooks plots, they're all reasonably clean in this instance. So again, confirming what we see with the history plots. We've got our fits. In this case, we have our individual predictions where I've plotted fraction, reporting cough versus dose, and each one of these panels is the different those different visits in here. So we go from the 4 to 8, 12, and up to 24-week visits in here. So you can see that, and if you want to see the time dependence, the same data is plotted then using the x-axis as time, where now the panels correspond to the different dosing groups. So we seem to be capturing both the time dependence and the dose dependence in here reasonably well. These are individual predictions. Now keep in mind what we're doing here is we make individual predictions for each patient, and then we summarize the individual predictions by taking averages over the treatment groups. Now we can do the same thing down here for our population predictions. Again, this is plotted versus dose or plotted versus time. Now the one thing that you'll notice in this instance, the individual predictions and the population predictions don't look a lot different. The 90% credible intervals are probably a little wider for the population predictions in this case. The reason the differences aren't more extreme is because, keep in mind, in both cases we are averaging over, well, for each one of these points we're averaging over 100 predictions. So in that case where we're taking means over 100 observations, the distinction between an individual prediction and a population prediction sort of vanish when we're taking averages over that many patients. And finally, there was that last plot I mentioned where I was doing this is a histogram of those individual specific E0 values. Particularly, I took the posterior medians and plotted those here, and then on the right side it's a QQ plot to compare it to the standard normal distribution. We see maybe a hint of some kind of skewing here in both plots, in here. So that makes one wonder. Also makes one wonder because this is simulated data, and it's data simulated using the same model we just fit. Well, actually, that isn't quite true. It's almost the same model. But it's essentially the same model, so it's kind of curious that there's suggestion of some deviation from the model assumptions here. Let's see, is there much more I wanted to tell you about it? Probably not. Probably the main gist I wanted to get across in this particular example was how to implement the random effect, how to implement a random effect in the in one of these models, so that we can do a mixed effects model. So that was the key, I think, the key message in here, and hopefully it was useful to sort of see see an approach for trying to think through some difficulties that are encountered in terms of the behavior of the MCMC samples, and how, at least in this approach, there was a strategy that alleviates it, but alleviates it at the cost of an additional assumption. So let me take a breather here, see if there's any questions about this. Okay. Well, just I'll give you a quick answer to that, Zhao. By the way, I'm guessing on your pronunciation. Hopefully, I'm not too far off on your name. You were asking how the highlighting. That's because I happen to be working in an environment. This is Emacs, a particular version of Emacs called Aquamax in the Macintosh, and there are some sort of language-sensitive facilities in here that automatically color code different elements of this. So that's why you see it. If you were in Windows, you can actually get versions of Emacs there too, and it's also possible to use this strategy there. See, not much cropping up, I see, but I guess one comment: if you haven't already attempted some of these problems, please do, because that's it's the best way to learn. Especially, it's the best way to learn by making mistakes, and then resolving them or getting help to resolve them. So, and I'd certainly be glad to help on that. I guess the only other action item I've got here after this session is I'll go back and remind myself what the heck X50 means in this context to make sure I've got that correct in this case. And I'll just respond in general. Let's see, what do we got? Okay, yeah, the question was, can I relate the model to non-mem terminology in terms of what is called pred and IPRED? Yeah, there's strong analogy between what I've been calling individual predictions, or predictions of new observations in the same patient, would be very closely related to an IPRED. The difference is we get a distribution in this case. We don't just get a point prediction. So in that sense, the Bayesian is a little different, but the core concept is essentially the same in there. Pred is a little messier. And I'm trying to remember, there actually is in non-mem 7 something that's more equivalent to what I'm calling population predictions here, and I haven't used it often enough to remember what the terminology was. But because anyway, the pred, of course, is what you get when you substitute a 0 in for your random effects, so that you're only using the point estimate of your parameter for doing your predictions. What I'm doing is more along the lines of actually simulating individual patients and characterizing the overall distribution of the predictions when you do that, so that now you have a predictive distribution that considers both variability amongst patients plus the uncertainty in the model parameters. So it's somewhat sort of like a pred, but not quite. Again, there is a I know that there's a simulation-based prediction that's now available in NONMEM 7, and I forget the name that they give it. It's not pred, but I think it still follows that same sort of concept in terms of naming, and that would be even more closely analogous to the population predictions that I've been using. Might call it I'm trying to remember. It might be called ePred, but I don't remember. Okay, well, if there's no more questions here, I'm going to vanish. I guess on Monday, I'm trying to remember what was next. I think what was next, are we jumping into count data, or are we not quite there? Let's see. Did our model comparison, all that. Oh no, we haven't really dug through the cumulative logit models for ordinal data, so I guess that's next on our agenda. So we'll be digging into that, and then and I'll be assigning another example that will be based on use of cumulative logit models. Okay, I guess I'll talk to you again on Monday. Bye for now.